So thank you, Scott, for inviting me here, and to Anna for making things happen smoothly. Um, I came once for a high-dimensional conference to College Station. That was like 8 or 10 years ago. This is my second visit to College Station, so I'm happy to be here. Today, I'm going to talk a little bit about what's called Henninger distance differential privacy. I'm going to structure this talk in a slightly different way. It's going to be some statistics, but I also want to give you the background of how this field emerged over a period of time and where the gaps are. So there'll be some math, but I have tried to play it down and make it like a story. So feel free to ask questions in between as we go along. And a lot of this work, at least the later part of the work, is with my PhD student, Peng Nan Deng, who also helped me put together this presentation because he was worried I would say things that are not quite the way he thinks. So I wanted to make sure that then I said, I'll better put your picture there. So with that in mind, let's just get started. So privacy has been a part of our world for a very long time. I'm going to start off with privacy post 2000 or 1996 when HIPAA came into being. And then there were lots of other regulatory ideas that emerged in the field that had an impact on how people did business. Since I work with people from healthcare organizations, I thought it's a good idea to understand some of the basics there. And then I thought, how did people do this before we talk about differential privacy? So today, if you go and did a Google search on differential privacy, it'll be very hard to identify how many papers there are. And if you do that 2 days later, you will see a lot more papers, and it's harder to keep up with the growth in the number of papers. That's an exponentially growing mechanism. So, but I want you to understand the basics and how people are thinking about these issues. And then I want to provide a slightly different perspective on DP, which is also there in the literature, but I'll try to make it a little bit more statistical from my perspective. I want to talk a little bit about robust inference. I've been working on robust inference, and one of the reasons I'm doing this is because there is a recent work by Marco Avella at Columbia and a few other people who have been thinking about robust estimation, M estimation problems, and how to make them robust. And my thought was that there are certain things that they have did very well, and I thought it's generalizable to more interesting problems. As a part of doing this, you have to study about how do you do optimization and keep it private. So it's a new subfield that's emerging called private optimization. But we'll talk a little bit, little numerical experiments, and then we'll end with concluding remarks. So to start off with, we all know about GDPR. Okay, is that good? Okay, thank you. Okay, so we all know about GDPR, and privacy actually started out, if you look at the history of privacy in the United States, around 1975 when you had the first law that came into being. And then there's a slow gradation in the regulatory requirements about how to treat personally identifiable data. That's the big thing. And today, with so much of data available, it is pretty easy to combine this information and identify people. So the question really becomes, how should, as a business entity, you handle this? Namely, there are requirements and there are strict penalties if people identify, especially if that happens to be a minor. So then the question becomes, how should the businesses do their work? And can they just go ahead and say, oh, I don't worry about it? Or should they take precautionary measures? So I'm going to, as I said, focus a little bit on the healthcare, especially with HIPAA, and that started around 1996. I think at that time, Clinton and Al Gore were the presidents and vice president. And then I think it went up to Obama's what's called high-tech Health Information Technology for Economic and Clinical Health Act. And that became big thing. All these things were, the goal of all these laws were not only to maintain privacy, but also allow all the healthcare organizations to adopt electronic tools, so to improve patient care. So they want to be able to say, when a patient's health information is available electronically, then they should be able to communicate. And if they communicate and there is some incident happening, then they should be able to go and get the required care without having to worry about, will this person allow me to use that data? Because so the question became, to whom does this data belong to? Does it belong to me, belong to you, or the entity that keeps the data? Okay? Or should it belong to the pharmacies, or should it belong to the hospitals? And if you ask anybody in the legal world and say, who does this data belong to? You will hear different answers. And there were some Supreme Court cases on this. And answer is, they don't know. So whenever they say, you will always say, wait a minute, talking about privacy, how can you have privacy without security? I mean, if I do a breach and I tell you there was a breach here, then possibly they can identify all kinds of information depending on what the breach is on. But then if I'm the one who is using your services to maintain your data, then you're going to come back and tell me, wait a minute, you cannot even keep my data safe. Why will I do business with you? So from a purely business angle, you're going to be asking the question, is it worthwhile to keep this business relationship with you if you cannot secure my data? So then you have to ask the question, how do I secure data? How do I measure the security of an organization? So there are small groups, several subgroups. Each group is trying to do their best. And each of them are trying to say, oh, I want to do this and this. I want to improve my patient care. I want to get access to this data. I want to be able to combine this data set with some other data set to produce this. But all these things you want to do behind a firewall. We used to think firewalls cannot be broken in, right? Think again. Now you can actually break through many, many firewalls. So then the question is, how does an organization really understand and protect data, maintain data privacy, maintain data security, and still adhere to several regulations that exist? So, well, when this was not enough, California said, oh, no, we are going to put in a newer law called CCPA. This became a huge thing. Everybody said, what a big thing it is. Every organization that was retaining data, they had to worry about CCPA. Pretty much often because the fines were extremely high. And if it involved a minor, you can forget about it. So the problem is that you may not be living in California. You may be living in Texas, or you may be living in Georgia or in DC. But if your organization touches the data from California, they have the right. With that strong rule, it became critical that, OK, we need to do something a little bit more careful before we say, OK, our data is safe. So this is all about the US. And Europe doesn't like to be left behind. And so they said, no, no, we want to have what is called GDPR. And we are going to make this even more harder to do business. So the whole thing evolved when I was in Georgia. And then there was this privacy officer named Lucy Doyle, who asked me, hey, Anand, we are looking for people to talk to about this. You're doing statistics and probability. Would you be interested in talking to us? And my answer was, wait a minute. I have no idea about privacy. I have no idea about security. So I don't think I can be of any assistance to you. So thank you, but no thanks. Then she was like, no, no, we are inviting people from different places. We want to talk to you and see how you can help us, if you can help us. So it wasn't a big drive those days from Athens, Georgia to Gwinnett County. So I just said, okay, I'll just go up there and talk to them. Then they talked to me about things. And I said, well, look, I don't have the knowledge to work for you guys, but I'm happy to think about it and see if I can help. That's how the whole thing started. And I said, okay, I want to start thinking about this project as a new project at the time. I said, I have never done this, but I thought it was exciting because the questions were very challenging at that point. And that's how I got started into this whole field 20 years ago, approximately. So you may always say, okay, let's go back to the law a little bit and think about HIPAA. In HIPAA, there are two parts called safe harbor rule and the statistical method, or they also call it the expert determination method. What's the safe harbor rule? Safe harbor rule will say, if you have a data set, you have to remove all of 18 identifiers, your name, your date of birth, your address, your social security number, your pharmacy record, all kinds of things. There are 18. And then there was a caveat that said, and any other remaining that could potentially identify the person of interest. So that was the catch. And when I talk to some of the legal people, they tell me, oh, that was just done by statisticians. So you just put in something that cannot be verified. So it's harder, so that you guys created a job for yourself. Having said that, there are not very many statisticians doing this on a regular basis. And so this is very stringent. If I want to do business, say I'm looking at people over the age of 70 who are taking this drug, mainly for patient care. And I want to understand how many of these people are taking a particular drug and how it is affecting them. Well, I need to know their age. If you say, no, you cannot share their age, then what good is the data to me? I cannot do anything worthwhile. So I definitely want to make sure that I have the age. That means I want to do analytics on your data set and do some additional work, but I'm not allowed to do it because the law says that you cannot take that information and do the work. But then there's a caveat, as always. It says, no, no, don't worry. If safe harbor method doesn't work, you can do the statistical method, where a statistician will write a certification letter that says the risk is really small to re-identify a patient or the person in the information. So from a practical angle, you can imagine right away all these companies running to statisticians or people who can do this work and say, hey, we want a cert letter. But then statisticians are a different commodity. They just don't write letters. They just say, we not look at your data. But then they cannot give you the data, because if they move the data to you, you are in trouble because you have liability on that data. So how do you make this all happen? So that's a tough question, right? So what did they do? Okay, let's see if we can de-identify this data. So you can say, well, I'm a statistician, but I really don't need to know all the other things. You just give me what you can share with me, and then I can tell you if I can identify a person or not, and then I can talk about the risk and so on. That's what we do well, and so that's what we wanted to do. So what did they say? Okay, let's do an aggregation. I will not give you data on every person, but I'll say all those people in Gwinnett County, in Georgia, for example, or in DC, who are in the age group 20 to 30, who are taking a particular drug, and then I'm going to say what their health conditions are. So you're giving information at an aggregate level, not at a single person level. Or you can tokenize. Credit card industry has been doing tokens for a very, very long time. Of course, they don't do things that healthcare does. So sometimes it doesn't work. You can suppress the information. You can mask the data. you can anonymize, and you can encrypt. And encryption is a little tricky because here, when you do encryption, you have to manage the encryption engine. Okay, so you need to know who can really look at this data. So that's kind of an interesting issue in itself. All these are big, big subfields within the data confidentiality area. And then what did you do? You say, okay, now that I have removed some of the identifiers, let me look at the probability of re-identifying an individual from your record. Or you can say, what's the information you gained about a person after looking at this data and without having this data? Or you can say, what's the predictive distribution? You can ask, okay, can I just add some noise to the data set so it's perturbed? And there is some work. All of this has been happening continuously. So there's a slow gradation. Okay? And around 2006, differential privacy was officially written as a paper by Dwork. So if those of you are going to the ICSDS conference in Nice, she's the speaker there. Okay, so now I'm going to move into differential privacy. What is our goal? We want to prevent re-identification of personal information from a statistic on a data set. So I'm going to say I'm not going to give you any information, but I'm going to give you a statistic value. I'll give you the mean. I'll give you the median. I'll give you the mode. Or maybe I'll give you the gradient of a loss function. So that's what we are going to be doing. And we want to do this in a peculiar way. I'm not going to give you the statistic by itself, but I am going to provide you a noisy version of the statistic. That means I'm going to perturb this data a little bit. And so instead of giving you the mean, I may say mean plus a noise. That's one way to do it. But then you want to do statistics at the end of the day. Okay, if you add the noise, I can add lots of noise. It's useless because you cannot do inference. But then you say, is there a correct noise I can add? So quote unquote correct. And then you can say, with that noise, can I still do inference? Will the inference be valid? And then can I quantify the amount of privacy in the data set? So those are the goals that we want to address. So if you want to think about it, think of data D1 and D2 as two databases. There are some queries that give you a statistic, and then you are going to apply a mechanism and produce an output, which is M1 and M2. So, okay, so your M1 and M2 are two outputs. So you can say, how good are they? And if I do a right thing, what I would like to do would be I want to understand the distribution. So these are the outputs. Remember, these are not the statistics you wanted, but these are the perturbed values. So I want to understand the distribution of the perturbed values. And if I say they're pretty close, that's going to tell me something. Of course, what it's going to tell you will really depend on what your D1 and D2 was, and I'll get to that in a minute. So now who is doing this? Your census is entirely doing differential privacy. IT companies, Google, Meta, almost everybody, they do differential privacy. And there's a caveat to this. I'll tell that at the end of the presentation. Few things you need to know about it. One is called adjacent data sets. So I said two data sets are adjacent if there's only one element different between the two. So, and there is a concept called a query function. That means you're querying the database. The query could be, give me the loss function, value of the loss function on my data set. The query could be, calculate the mean. Tell me the proportion of smokers in your data set. All kinds of things. Give me the proportion of people who are taking this PrEP, which is one of the highly used drugs amongst various people. So, and then you say, what's the mechanism I'm going to use to ensure the data is perturbed correctly? So that means I have to tell you, how do I perturb the data? Okay, one thing you can do is I can do some noise. So the original noise that was used was the Laplace noise. And then they changed it to Gaussian. And now there are different ways you can add different noises. There is something called an exponential mechanism, which includes the additive mechanism, but you, instead of adding a noise, you generate data from a distribution. And this is a department with a lot of Bayesians. And so you may want to say, I want to generate posterior distributions after adding this one. It's called the exponential mechanism, okay? So you can immediately generate data from the, just to emphasize, these are all conditioned on the data. I want to repeat this, okay? These are all conditioned on the data. Then you can say, well, I just want to focus on the top k of them, or I can say give me the percentiles, or I give you randomized responses. You have to be careful when you do the randomized responses. If you say, I'm going to randomize when the person had a surgery, that's a problem. So everything will not work in all settings. So what you choose will be different for different data sets and different use cases. So what's the basic idea behind a differential privacy? The basic idea is that you start with some query that you are interested in, identify the sensitivity of the query. How sensitive is this? And then you ask, how do I perturb this data? And then I release the perturbed output. Let me repeat this. I'm only sending out the statistic. In lots of places, they don't really want the statistic. They actually want the true data set. Okay? And that's called synthetic data. And that's a whole different topic. We are not going to get into that in this presentation. Here, I'm only going to release the statistic, namely a perturbed mean, for example. So the picture goes like this. There is one element which is different here. Just one record is different. You have a query function, and then you have a statistic, T1, and then you put a mechanism, and you have outputs M1 and M2. So what does this tell you? If I change one element in my database, and if the distributions M1 and M2 are very similar, then probably I cannot find out whether you are in the database or not. And this reflects the idea of robustness, statistical robustness, right? That's what robustness is all about. You say, oh, is there an outlier? Is it really affecting my output? Is it really affecting my inference? That's exactly what's happening here. You can say, I have a record. They're just different in one item. And now I just did a perturbation. After perturbation, if the distributions are not different, then I do not know whether a particular element was there or not, right? Okay. So let's now focus on the simplest case for today's presentation. It's just going to be on the additive mechanism. So I'm going to choose a distribution, Gaussian or Laplace. And I want to know how indistinguishable these two adjacent data sets are. You could ask me, can I change it to K? Yes, you can. That's called as group privacy, and we can do all of that. But let's focus on this today. And we can measure this. How close are these distributions? So you can say, well, I'm a statistician. I'm going to think about Kullback-Leibler. Sure. You can say, I can also do other distances. You can do other divergences. There are so many things, right? That's what's so special about one divergence. So what I'm going to do is use divergences for this. So if you do not know a priori, divergence between two densities, probability densities, is a function d. It's not necessarily a metric. It's non-negative, and 0 if and only if p equals q. It will not satisfy typically the triangle inequality. Okay? So Hellinger distance is a metric. Square of the Hellinger distance is a divergence. So the original work was from Dwork, and she said, well, look at the probability that M1 belongs to a set divided by M2 belongs to a set. And if I can choose my mechanisms so that the outputs of this ratio are all possible values of the data set. That's the key here. For all possible values of the data set are less than epsilon, then I get what's called max divergence. And you can relax it a little bit by adding a constant delta. So this is the most familiar way in which you would have seen it if you have seen DP before. The most familiar way is to say, if you look at the ratio, you can think of it as a likelihood ratio. It is just approximately 1. So small values of epsilon means you have very high privacy, and high values of epsilon means that it has a very low privacy. Now, I'm moving towards Renyi divergence. Okay, what's so special about Kullback-Leibler and Max divergence? Let's just spend a little bit time about what's called Renyi's differential privacy. So I'm still interested in measuring the distances between densities. And this is called the Renyi divergence. This was actually developed way long ago, 1952, if I remember the first paper on Renyi divergence. It appeared in somewhere in a Hungarian journal. And so it is just nothing but the ratios of densities of the two outputs. I want to re-emphasize that these are the outputs, okay? And then you are going to raise it to some power alpha, and then you have divided by alpha minus 1. And if you take the limit as alpha goes to 1, then you get back the Kullback-Leibler. So a few years ago, I think 18 or 2017 maybe, there's a paper by Dong et al. And they said, wait a minute, this privacy problem can be treated like a hypothesis testing problem. You are just trying to show if two distributions are close. If I can show the power to, I'll fix a type 1 error alpha. I'll fix a type 1 error alpha and ask the question how hard it is to distinguish between normal 0 and normal mean mu. And then you ask the question, if the power to detect FM2 against FM1 is smaller, that is at least as hard to detect this, then I get what's called mu GDP, because here mu you think of as the hardness in detecting the difference from 0. Clear? So this is an alternative way to think about privacy. So you are asking the question, how hard it is to separate normal 0, 1 and normal mu 1 in a given data set. I know there is a power. We all know that power. You can calculate that power pretty easy. And then you ask the question, is that power larger than FM2 and FM1? If it is so, then you say that I have mu GDP, because mu here represents the hardness in detecting this difference. So today we are going to talk about Hellinger distance. So I should at least introduce the formula for Hellinger distance. And this is the square of the Hellinger distance is just you put a square root on the densities and square them, and that's it. And I say a mechanism M is said to satisfy epsilon HDP if the Hellinger distance between the two outputs is less than epsilon. You choose the epsilon, okay? You choose the epsilon, and then you want this to be as small as possible. There is a related concept called the power divergence. So this was done a long time ago. People have been doing power divergence. One of the good references is Bruce Lindsay's paper on power divergence or case for robustness. There is also a paper by Cressy and Reed, who used power divergences to understand, do hypothesis testing in the context of multinomial distributions. So that's where these power divergences come in. So it's essentially the same thing, but with a power lambda plus 1. And you can notice that this power divergence can be written in terms of Renyi divergence for lambda positive. Okay? For lambda negative, you cannot do that. So you can say, instead of looking at Hellinger distance, you can say if the power divergence is less than epsilon for a given lambda, then I say it satisfies lambda epsilon PDP. When lambda equals minus 1/2, you get 2 times the Hellinger distance. Okay, I'm going to skip this part, but I'll come back to that a little later, okay? Now you can say, wait a minute, you introduce your own methods of defining privacy. How do they relate to what's already there? And you can say immediately, if I have HDP, then it also satisfies DP, namely standard differential privacy that was done before. And you can say, if it satisfies epsilon HDP, it also satisfies mu GDP. Now, how good is this output that I produce? You gave me a statistic, I perturbed it. Now I'm not going to just sit with it and be happy. I'm going to do additional things. I'm going to modify it. I'm going to combine it with something else. That means I want to do more things with the statistics you produced. That means I'm going to post-process the data you give me. So there is something called a post-processing property, which says that if I have epsilon HDP, then the post-processing property says that if I do some reasonable things, they will also satisfy epsilon HDP. Okay, that's the key idea here. So if you cannot do that, then all of this is a waste of time. Okay, how does it work in industry? Let's go back to that a little bit. I said, so I am a person who holds all the data that goes between various clients. So what am I going to do with this data? So she comes to me and said, hey, I want to buy a data set from you because I have some analytics I'm going to perform. I have funding for that, and I'm going to create a new product that's very useful for people having cancer. So I said, okay. And she said, I'm going to only focus on melanoma. He says, no, I want to focus on breast cancer. And he says, no, I want to focus on, say, brain cancer. So all these people want data from me. I am the one who is maintaining the data. And remember, if I keep all the data, it's useless. Number one. Number two, I have to keep putting money to maintain them. I have to store this data. So I need to employ people. That means that I would like to sell this data to some other people so they can use it, and that I can even invest more and facilitate this process. That's where the commerce comes in. And this is useful. Okay, it's not like I want to throw them away. I want to facilitate commerce, and my job here is to ensure that if I give this data to him, and to her, I want to be able to say, overall, what is my privacy? Well, remember now, if they're all on independent data sets, then I can say, well, what's the worst case? That's called as parallel processing. But you see, sometimes people have both melanoma and maybe they also have some other cancer. So they need to look at those things. So that means same data set being sent to two different people. They're going to do two different things, which means the privacy guarantees I give you is going to reduce. That means it's deteriorating as I keep increasing more and more customers. But I'm in this business also to make profit. I want to do good things to people, but I'm also here to make profit, which means that I would like to have more customers. That means there's going to be more and more problems. So what the processing rule tells you is that how do I identify the overall privacy level after compositions, sequential composition, or parallel composition, or an adaptive composition where I first give her this data. So what he does is he took my data, looked at her data, and took that information and put it into his model. So there's a cross contamination going on here, and you want to know what can I say about that privacy. And that is the so-called adaptive composition, also called as advanced composition in the literature. Okay, so this is all we want to talk about privacy. Now I want to go to something statistics, and I want to say, can I do this in real time? What things I have to worry about? So I've been working on Hellinger distance theory for a long time, more than 15, 20 years. So I wanted to say, okay, if I have an IID data, very simple, right? I know how to do robust and efficient inference. You can do, say, I want to talk about M estimation, and you can do that too. There is a reason to do Hellinger distance because this is not only going to be robust, but it's also going to be efficient. When I say efficient, I mean when the model is correct, then the limit distribution will have Fisher information as the limiting covariance matrix. Okay. So let's skip this part. It just tells you that there is an asymptotic distribution. If the model is correct, then you get the true estimate. How am I doing on time? Okay, perfect. Say it again. before? It's just a parameter of your model. So you have a parametric model. It's indexed by theta. So if you're thinking for normal distribution, you can think of just mean and the variance, but it can be very general. Okay. But finite dimensional for today's talk. So I want to estimate theta. How am I going to estimate? I'm going to minimize the Hellinger distance between my non-parametric estimate of the data, say kernel density, for example, and you take f theta, and you say, I want to minimize that. Okay. And what this says is that if you do the standard things, you output family regularity, then you get normal distribution with some covariance matrix, and this covariance matrix has this form. And you can say that if the model is correctly specified, this is actually the Fisher information. This is classical. Okay, this is classical. There's nothing new here. Now, my goal is to add an additional word to this: robust, efficient, and private inference. That means I want this to be private. The estimator I release will not be theta hat n, but it will be a private version of theta hat n. Okay, so first you say, okay, fine, that's all good. First tell me, how are you going to calculate your estimator? Well, we know there are not too many techniques that you can use. When you see this, immediately say, well, I am going to use Newton-Raphson. And you can also use gradient descent. The interesting thing about gradient descent is that for it to work, you need to have strong convexity properties. At least that's what people believed. There is an emerging research that says you may not need that much. Because a lot of times you will hear people say, yeah, but it still works though. It's not convex, but if you run it, it works though. It gives me that number. I did Newton-Raphson. They're pretty close. And you ask, why did that happen? So does that mean convexity is not really required? Or is there some weak form of convexity that is sufficient to give the answer? And then, of course, the question is, if you give it the algorithm, how do you make it private? Oops. I'm going to tell you. That means I'm not going to give you. So going back to this, you wanted the mean x bar. I'm not going to give you x bar. I'm going to give you a perturbed version of x bar. So here private means I'm not going to give you the minimizer. I'm going to give you a perturbed version of that. Okay, that's the private. Okay. All right. So first you have to identify a mechanism. And I say, I'm going to use an additive mechanism, which means I'm going to add noise. And I want to use a loss function, which I will do. And I have a statistic theta hat n, which is the minimizer of this loss function. In this case, it is the Hellinger distance. And I want to say, we will immediately someone will say, why don't you just get that estimator, add some noise to it, and get it done with it? What's the big deal? To do that correctly and say I have so much guarantees, I need to know the distribution of theta hat n. Unless you are in a very special case, you do not know this. Okay? So the alternative would be, can I integrate this into my algorithm and then build an estimator? So what's the idea? So I'm going to say how to do private gradient descent. I'm going to say, choose a mechanism. You can use an exponential mechanism as well, but we're going to focus on the additive mechanism. Determine the number of iterations you're going to do. It's very critical here. Identify a query, and every iteration calculate your sigma. Namely, you're going to add a noise. Let's say you're going to add normal distribution. Say I know the mean, and then I'm going to add some noise, so I need to know the variance. So what is the correct variance that I can put in there so that I can get this HDP property? Namely, if you measure the Hellinger distance between these adjacent data sets, then they would have be less than epsilon. And return the updated estimator. Yeah. Okay, so smaller the epsilon, higher the privacy. How small an epsilon you want depends on how conservative you are. So from purely commerce perspective, where I would like to apply this, my role would be, I want to do more business. Then I would like to relax my epsilon Okay, not close to 0, maybe closer to 2, maybe 1 or 0.5 or 1. And if I do it that way, then I can maybe do other things. So this question is very relevant because I want to emphasize here there is also simultaneously a contract that goes on. You don't just give this perturbed data, there's a contract. In the contract, you'll have to say what you're allowed and not allowed to do. So your use case becomes part of choosing epsilon. But if you say, no, 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 I want it to do whatever I want, then I'm going to say, well, in that case, you have to work with what my company allows me to sell you. Okay, so I may not be allowed to sell more than 0.03. Okay, so it really depends on. Okay, sorry. And then return the updated estimator. So what would be my mechanism? So I can think of this as I choose the value, initial value, take a learning rate eta, and then look at the gradient of the loss function, add the noise. This is what you're going to do. So now the question is, how do I calculate the sigma so that the updated estimator is epsilon HDP? So that means I want to make sure that the Hellinger distance square between adjacent data sets, PD and PD prime, is less than or equal to epsilon. What is my PD? You can think about it. This is normal. I'm fixing the data set. So this is normal with this mean and some variance I don't know yet. And then I'm going to say same thing on an adjacent data set. That means I'm evaluating the loss function on the estimator on 2 data sets where 1 unit is different. And then I'm going to go ahead and calculate this, and I'm going to take this over all possible data sets. That's the idea here. Is the idea clear to everybody here? This is the punchline of this presentation. So this is where you actually say, how do I calculate sigma? So 90% of the work here is calculating sigma. So let's go through this. If you do this calculation, this is if you take any 2 vectors, mu1 and mu2, and say I want to look at the Hellinger distance between them, this is a standard calculation that tells you this is of this form. Here I notice that this is the gradient of the data set, D. So D is fixed. Again, I want to emphasize that D is fixed. And here is sigma square. I want to choose sigma square so that this is bounded by an epsilon. And here is where I'm going to use how much privacy budget I have. Overall, I told you I have epsilon privacy budget. And I told you have to predetermine the number of iterations, which is k. So that means that every iteration, I am going to give you epsilon over k. That comes from the following property, which I didn't emphasize too much in the previous picture. Yeah, here. So when you do this mechanisms, you notice that there is an output which gives you the amount of HDP. So this is the serious issue here. You need to calculate that. And here you can show that it is bounded above by epsilon 1 plus epsilon 2. And here again, it's bounded above by epsilon 1 plus epsilon 2. OK. Now is something important I want to emphasize, which again I skipped over before for obvious reasons here. So you can do this game not just for Hellinger distance, you can do this for any power divergence. So if I do any power divergence, then I'm going to get this sigma square, which depends on lambda and epsilon. But I'm a statistician, so I want to emphasize how do I do this. So I want to minimize this variance over all possible values of lambda, and that happens when lambda is minus 1/2. That's why we are talking about the Hellinger distance. Okay. So, and if you do this algebra, you immediately notice that your sigma square is this. So every time you generate a new IID random variable with this variance, and then you go ahead and obtain your estimator and release it at the kth stage. And you can do the same thing with the Laplace mechanism. The math is a little complicated when m is large, but we can do it. So how does this work? It works as follows. If you're doing the standard gradient descent, you're starting here, and then you're going down like this. This is where you're going. When you're doing a private version, you have first you go to theta 1, you go here, and then you add more noise, you go here, then fine. This is different from the value theta, which you will be releasing. So if you do a typical trajectory, blue represents the classical analysis, which is not private. Red represents a private version, which will go up and down because of the noise you're adding. And you can do the same thing with private Newton. And this decomposing the privacy budget is coming from the composition property. So now you ask the question, how good is this? So how do I measure the utility of what I produced? You can say, well, I can do this in two ways. I can say, how close am I to the non-private version? So it says that if my sample size gets very, very large, I can basically show that this difference will go to 0. But here I want to emphasize this k that I have will depend on n. For gradient descent, it behaves like log n, whereas if I do Newton-Raphson, it behaves like log n. So the number of iterations I do is higher for a gradient descent that you should expect. And so for the Hellinger distance estimator, now what people wanted to do was, everything I said so far works exactly similarly for the M estimation, but there is one issue that in delta n, the sensitivity, how bad this is, the data is between two adjacent data sets, that's 1 over n, whereas in the Hellinger distance is of order 1 over root n. That's a problem because when I'm calculating this estimator and talking about the efficiency, you notice that this is not going to be true if I do the whole comparison. Think about it. If I'm doing differential privacy and I say I'm going to compare two data sets, they can take very, very, very large values. So when you do M estimation, what they do is they do Huber's loss, which means you truncate the score function beyond some point, and so you get a bounded score. Once you bound it, everything will just go through. In Hellinger distance, you cannot do that. It does not allow you to just truncate it if you want to retain privacy, if you want to retain efficiency. So we needed to introduce some new techniques to say how fast they can go, and that's what we did in our paper. So a quick and a brief numerical experiment. We did this just on a normal distribution. We have done extensive simulations using various distributions and so on, but I'm going to present only here. So epsilon equal to 2 means there is no privacy. Okay, epsilon is 0.6 is more privacy. 0.2 is even stronger privacy. So if you do this, and you notice that our estimator pretty much retains for the mean, and the coverage of the confidence interval is reasonable. I would say as you increase your decrease your epsilon, you notice that the coverage does come down, and you expect that. And I personally am not affected by it. I don't have a problem with that because if I'm wanting my estimator to be private, I would rather it doesn't have high coverage. Okay, just I want to emphasize that part. And you can do the same thing for the for the variance. And so this is just a private gradient path. We drew the 75% quantiles or the percentiles along every path. You notice that they are pretty identical. They are very, very close. And we are doing here 30 is the magic number. 50 is the magic number. And I want to show one more picture here. And this is actually the trajectory. How did this gradient descent work along a trajectory? If you look at it, notice that right at 30, they pretty much don't decrease any much. So around 30, I have a pretty good result. I could have stopped at 30. Going beyond 30 into 50 because they determined that 50 doesn't add anything to my final estimate. So I could have stopped at 30, but I just wanted to show the whole thing. So it is okay to do that, but remember at that point, your privacy is also different, okay? All right. Am I doing? Yeah. So the concluding remarks, we introduced a new metric called differential privacy metric called Hellinger differential privacy. We described the private version of the gradient descent and Newton-Raphson methods. We are also currently looking at the more general interior point methods, which are fascinating because they work in a very different way. We have established the utility and efficiency of our estimators. what we're trying to do is, so if you look in the current work, this is more general. People have always worked with random variables with bounded support. You may frequently be looking at random variables with unbounded support, very high dimensional problems. In those cases, the methods don't carry over. The math doesn't carry over. In fact, most of the work on that is the most important thing people are doing. And one more thing people really are looking at is what is called user level privacy. This is all at the corporate level privacy, if I want to say it. You could also reduce it, say, what privacy do I lose because you did this? We're looking at those questions. Some of these are very philosophical. What should you know about me from a data that I didn't share with you? If you picked up something about me from my Facebook post or some social media post, that's a different story. And how do legal things overplay with these basic privacy regulatory requirements is still unknown, and it's an emerging field, and we're looking at some of those questions as well. References, and I want to thank you for your attention. Thank you.